Hello, good day, guys. Thank you for joining. This is the Adobe Fikemba. I told you in this channel I'll teach you physics, chemistry, and biology. Earlier on we discussed chemistry. Now we want to look at physics. Okay. So in physics, if you've not watched the video, before you catch up with the video or you see what I'm doing, well, it depends on your level of exposure. Go and watch from the beginning, from physics part 1 to this very moment, so that you can have a better understanding step by step how these topics have been treated. So today we're looking at equivalent units and quantities in physics. So discussing physics, we're looking at equivalent units. Okay, so we're looking at physics. This is Adobe Fikemba. Okay, I got you guys covered. I'll teach you these 3 subjects by the grace of God. Physics, equivalent. We're looking at equivalent what? Units and quantities, okay? Quantities. In the previous, we've talked about, previous videos, we've talked about what measurements are, units and quantities. We give example. We looked at fundamental quantities. They are the base, the bedrock in physics. We looked at derived quantities outside the fundamental quantities. The fundamental quantities are 7 in number. We stated them in the previous video. Go and watch it. You see all of that. And then I give you about 20 examples of derived quantities. Now I want to look at some quantities that have they have equivalent units and quantities. Okay. Now, what are equivalent units? They are units with similar dimension or the same dimension. Okay. That is what equivalent units and quantities is all about. They are units with what? The same dimension. When you talk about dimension, you're talking about an aspect that deals with the measurement of those quantities. That's what you're talking about. So let me quickly give you examples of quantities with what? Equivalent units. So let me just tabularize it so that it will be very easy for you. But they are the same thing. So examples. So yeah, I'll just write examples, okay, of equivalent. Equivalent means the same. Equivalent what? Units. Let me just summarize it out, okay? So examples of equivalent units or units with the same quantities or dimension as the case may be. So here, number 1, okay, we have impulse. Or let me not tabularize it because I'm going to make a proof. I'll prove some things for you. So sorry about that. So number 1, let's start with impulse. Impulse, okay, its unit is newtons seconds. Okay, and then we have momentum. I'm going somewhere. Momentum is also the same thing with this, but momentum, we can write it this way: kilogram meter per second. Now look at this now. The reason why I said I didn't want to tabularize is because if I tabularize it, I might not be able to explain and prove to you why this and this are the same. I'm not in a hurry. That's why I started this way. I want you to understand, because when you understand, you become outstanding. You don't cram, understand. If you understand, you will not struggle to give answers. So look at this now, impulse. Now, if you remember this formula, okay, if you remember, this is Newton seconds. If you remember this formula, F is equals to m bracket v minus u over t. If you cross multiply this, that's where impulse is coming from. Okay, do you see it now? Which is what? Ft will be equals to what? Mass bracket v minus u. This is the impulse. Force, the product of force and time. That's the newtons seconds. Do you see it now? That's why I want to use this to explain. Now, if you look at momentum is the product of its mass and its velocity. I've not finished. Just follow me. I'm going somewhere. Momentum is the product of what? Mass and its velocity. Look at kilogram is representing mass. meter per second is representing velocity. Are you seeing it now? Another thing again I want to bring for you here, Newton. Newton is represented as kilogram per meter square. Now, kilogram per meter square is used in representing Newton. Now, when we say this unit and this unit are the same thing, you'll see we'll get the same answer. Now, since this is kilogram per meter square times this seconds, S, can you see it now? That's why we put this S here, which will still land back to this. Now, you know, according to the law of indices, that's why you have to be inclined in mathematics to be able to be a complete science student. It will help you. Now, look at kilogram, meter. This is S raised to power minus 2. Do you know this thing is also S raised to power 1? So when you look at this now, you have kilogram, meter per second square minus 2 raised to power 1. No sign means that's plus 1. What does it give you? It will be equals to kilogram. Are you seeing it? Okay, good. To be kilogram meter per second what? Minus 1, because minus 2 plus 1 will give you what? Minus 1. So you can see that at the end of the day, from these Newton seconds, we're able to derive kilogram meter per seconds, which is equivalent to this guy. Do you understand it? Do you understand it? So you need to understand why impulse has equivalent units as momentum. You don't just cram and just think, oh, they wrote it that way. You don't know why. So I've been able to explain why for you. Do you see it now? Impulse is the product of the force and the what? Time, which is Newton seconds. This Newton is broken down as kilogram meter per second square. When you add this T, the SI unit of time is seconds. Seconds, S raised to power 1. Why this minus 2? Since they have the same base, okay, according to law of indices, the same base. Now the powers, this is times, you add the powers. So I added the power, minus 2 plus 1. This is still plus 1. Plus times plus is plus 1. So it will now be S raised to power 1 minus 2. That's how I got this. So you can see this end product and this here is the same thing. Do you understand it? If it's clear, write copy in the comment section. Let's go to another one again. Okay, another example of equivalent units. We have velocity and speed as another example. That one is direct, so I'll clean this. Okay, let me just write that one here. Number two equivalent unit is what? Velocity. And what? Speed. Both of them are meter per seconds, meter per seconds. But tell me, what's the difference here? Who can tell me the difference? The difference is that velocity is what? Vector. Why this guy is what? Scalar. Okay? Take note. Velocity is vector. Speed is what? Scalar. Okay? This is the rate of change of displacement. Why this one is the rate of change of distance. Is that clear? Why this would be V equals to X over T. This would be V equals distance over time. Do you understand? This one will take this sign, letting you know that's vector. Okay? Is that clear? But they have the same units. These are equivalent units. Another one again we have is number 3, pressure and tensile stress. Number 3. So I'll clean this now. Are you getting something? Okay. Number 3, we have pressure and what? We have pressure. So I'll clean this, okay? I believe you can stop the video and watch and write yours. Pressure and tensile stress. So pressure is Newton per meter square. Tensile stress is also Newton per meter square. What's pressure? Force. Pressure, P, is force acting per unit area. This Newton is coming from this force. Why this per meter square? Because of this over sign. Area. Area is length times breadth. Is that not so? That's why you have m raised to power minus 2. Once you see this over sign, it will give this guy a negative sign. Tensile stress is also, when you want to look at tensile stress, when you're talking about Hooke's law, elasticity, as the case may be, you're looking at a situation whereby it is that that force that causes a deformation, okay, the agent of deformation, that's the stress. But mathematically, it is represented as the force acting on the cross-sectional area of the material. That's why it is like this. Can you see it now? That's number 3. Then we also have number 4. We have surface tension. Okay, we're looking at equivalent unit. And what? Surface tension and force, spring constant. Spring constant. Okay, these two have equivalent units. Surface tension is force acting per unit length. So it will be Newton per meter. Have you seen that now? Newton per meter. This one too, Newton per meter. So if you look at it, surface tension is force per length. Do you understand it? While spring or force constant is K equals force acting per unit extension, where this extension is representing the meter. Do you see it now? Because if you remember this formula, F equals KE from Hooke's law. So if you are looking for this spring constant, it will now be K equals F over E, which is force per unit length. Do you understand it? Is that taking? Okay. The next one, number 5, let me just make it 5. Number 5. So I'll just clean this. Is moment and work. Number 5 is what? Moment and what? Work done. Moment and work done, or energy. They have equivalent units. What's moment? Newton meter. What's work done? Joule. What's energy? Joule. Are you seeing it now? If you look at the definition of this guy, work is the product of the force, okay, with a distance of a body that moves in the direction of the force. So work is equal to force times what? Distance, which is the same thing as Newton, and this one, meter, is equivalent to this. Do you see it now? Can you see it? Do you understand? So moment is force times distance. Work done, force times distance of the body moving in the direction of the force. Do you understand? What's energy? The ability to do work. If it's the ability to do work, it's also joule. Do you see it now? So with these 5 examples, we've been able to look at equivalent units and quantities. Let's quickly look at dimension. Dimension, quickly. Dimension. Now, one important thing about dimension is that, of course, when you're talking about units, you must mention dimension, okay? Or you're talking about fundamental quantities and derived quantities, you must talk about what? Dimension. Is that clear? Now, in this case, dimension is used to compare two or more physical quantities, as the case may be. And it can be used to test the validity of a formula, okay? It is used to test the validity of a formula to give us what we call dimensional homogeneity. In the next video, we are going to look at, don't look at the timing, pay attention with your understanding, more important. I will just write the dimension and I will stop this class. The next, this thing we're going to look at, we'll look at calculations involving dimension, how to solve it. So let me write some dimensions for you. Whenever you see these things, know that is what it is, okay? So I'll just write quantities here. Then here I'll write dimension. So number 1, we have length. Dimension, anytime you see length, represent it as L. 2, you have breadth. Represent it as L. 3, extension. Represent it as L. 4, radius. Represent it as L. 5, distance. Represent it as L. Do you understand what I'm saying? Anytime you see any of these things being written or asked as question, their dimensions is represented as L. Is that clear? Number 6, when you see time, represent it as capital letter T. Number 7, when you see period, represent it as capital letter T. And number 8, the last, when you see mass, represent it as capital letter L, M. So capital letter L will give you all the dimensions for length, breadth, extension, radius, distance. Let me add one more here. So let me just say 5, 6, diameter. Sometimes they add that 7, 8, 9. So I give you 9. So L. So once it is L, T, T, M. So once it is length, breadth, extension, okay, radius, distance, and diameter, use L to represent anything about them. When it is time, period, and mass, use T for time and period, and capital letter M for mass. I will see you in the next video. If you're not following me, follow me so you can see more videos. You can learn step by step, and you can conquer WAEC and JAMB, or whatever any foreign or external exam body. Thank you, and see you in the next video. Thank you.